Well, welcome everybody to the session on implicit modeling, which I'm very pleased to see. We've got a few implicit modeling papers. The history of implicit modeling is that we had a separate conference series called Implicit Surfaces way back in the 90s, and then we merged with shape modeling, and the rest is history. So, but I'm very pleased to see the area is still very active. And of course, having been retired for the last years, I have not read any of the stuff on neural implicit. So I'm very interested to hear the first speaker from India, which was certainly not one of the countries interested in this modeling back in my day. And it's very good to see that there is more discussion context. Otherwise, we just see in the French. So, Bincy here is going to be our first speaker. Bincy Antony, co-authored with Ramanathan, I'm going to get this one, Muthuganapathy. And he's going to speak on some of these neural SDFs, which I'm very interested in. Go ahead. Do you want this one as well?
No, I can use this. Good afternoon, everyone. I'm Bincy Antony from IIT Madras. My advisor is Professor Ramanathan Muthuganapathy. Welcome to my talk on BBSDF, which is focusing on creating generalizable neural SDF and medial access extraction from the learned field. So our input is unoriented, noisy 2D point sets. We assume no connectivity, no normals. Our aim is to learn SDF and then extract the medial axis. So before I move into the details, I would like to discuss what sign distance field is. A sign distance field assigns for each point its shortest distance to the boundary, with the sign indicating whether the point is inside, on the surface, or outside. So it is computed using this equation. It is straightforward to compute the sign distance field for analytical shapes like circles, sphere, etc. For example, for a circle shown here with center C and radius R, solving this equation will give us a value of negative sign distance value for a random point R, 0 for a random point R on the boundary, and positive for a random point R outside the boundary. So this shows the heat map representation of the sign distance field for a 2D circle and a 3D sphere. The difficulty that we face is we do not have a continuous boundary like this for which we can find the exact distance value. We have this kind of sampled points. For a random point R, the shortest distance shown by this black curve, that point is not even there in the sampled points. Another difficulty is we do not know the inside outside. So we can only find an approximate distance shown by this orange curve. So this becomes an approximation. So one can think of reconstructing the boundary and then computing the distances, which again becomes approximation. So here I show a 2D point set along with the approximated boundary. So this approximation itself is hard when the boundary is noisy. So as can be seen here. So hence our aim is, given a noisy point set, learn the sign distance field and then extract the medial axis. Currently, there are few approaches for learning sign distance field, but most of them are per shape optimization network. So they fit one neural network per shape. Hence, they are very slow and do not generalize to all shapes. And moreover, as we saw in the morning talk, they focus on surface reconstruction accuracy (SDF) on the surface. So leaving the interior SDF that is not given much attention. So our aim is to learn the interior SDF accurately because that is what we need to extract the medial axis. And currently there is no public data set with accurate full domain SDF supervision that can enable us to learn the sign distance field. Because people usually rely on regularizers like iconal, Lipschitz, neural pull loss, etc. But they are very slow. Our aim is to make faster network even in terms of training, because we do not have big computing facilities. So we couldn't rely on all these slow regularizers. So we wanted to rely less on regularizers and rely more on data. So this is the aim. Given a noisy point sets, instead of taking this geometric route, this shows a Voronoi based skeleton. Instead of taking this geometric route, we go to the sign, learning the sign distance field, and then extracting the skeleton from it. So the key contributions are an SDF dataset, which is a diverse 2D point set with accurate point to curve ground truth distances, and then a generalizable neural SDF architecture, which focuses on locally conditioning the network and hence predicting accurate, far from boundary sign distance field, and then a medial access extraction algorithm from the learned field. To create the data, we represent shapes using B-spline curves and then solve the constraint equation and then take the minimum distance to get the sign distance. So this shows an example of our data creation process. Here I have shown one shape using a B-spline curve C of t. Then for a random point r, we solve this constraint equation to get all the candidate point, and this is the minimum. This is the one with the minimum distance that becomes the precise sign distance for that particular point. So this shows for a point r outside. So this shows our we have shown for 1,000 samples the sign distance value. This shows the heat map representation of our ground truth data for one sample. Following this process, we created 1,176 curves and we store them as boundary points, 1,024 boundary points and 50k random points from inside, outside and on the boundary, which serves as our ground truth data. So this is the algorithm that describes the data creation process. Then we created a generalized neural network architecture. So what we do here is, given a shape, we encode it using this network, and this goes to a feature grid. And then when you want to predict the sign distance for, let us say, a query point Q, you sample the feature grid at that location. So this will give a local context of what that shape is. So now you have conditioned that point on the shape itself. Okay, now this shape information, so this is the shape information, which is a feature vector, along with the points coordinate xyz, xy in this case, at that point is Fourier encoded. These two are concatenated and given to a multi-layer perceptron, which predict the sign distance value at that point. So this is trained on all the 1,176 training shapes that we created. So you can see the predicted sign distance field already has the medial axis coming out of it. The divergence of the field is used to create a score using which we extract the skeleton. This algorithm explains the SDF, the skeleton extraction process. So these are our results. We are shown as 3 columns. The first is the input point set. Second is the predicted sign distance field. And third is the extracted skeleton from it. We have shown for various shapes like organic shapes, thin structures, junction cases, high curvature, etc. So this shows result for shapes with holes, which was not even present in the training data. You can see blue represents the sign distance value for shape in the inside, and red represents the outside, and from which we extract the skeleton. So it may be noted that this was an out of generalization data. We never saw this kind of data during training. So this is a comparison with existing neural approaches, the neural skeleton, the deep medial field. This grid-based approach is not a neural approach. It is the usual grid approach of finding the distances, a one Lipschitz approach. And this is our method. This last column shows the ground truth. You can see in various noisy configurations and outliers, and even in missing regions, we could produce stable sign distance field. The neural approaches are also good in predicting the sign distance, but grid-based approach fails in presence of noise. You can see this result. So, major drawback of the per shape optimization approach is their time required. We predict in one forward pass in only 0.18 second, while most per shape optimization approaches require multiple iteration because they fit one neural network per shape. So it takes from 5 seconds to hundreds of seconds to predict the sign distance field. So this is one comparison with the classical Voronoi-based approach. In presence of noise, clearly they produce many spurious branches, while our approach is producing stable field, and hence skeleton extracted is stable for different noises. So this shows a result on different boundary sampling strategies. This result shows that we are the predicted sign distance field is insignificant to the type of sampling that you make. This shows a study done on the effect of number of boundary samples used for prediction. We are robust to the number of samples. Even at n equal to 128, you can see we produce coherent sign distance field. So this is an important ablation study that we did. This shows how ground truth supervision is helping us to predict the sign distance accurately. The first study is using the iconal optimizer with only boundary supervision. The second is supervision is provided only in a narrow band near the surface. You can see the quantitative matrices. Clearly, our approach has lowest SDF L1 error, chamfer distance, and the gradient field is close to 1 in our case. This shows the same qualitatively. The truncated SDF focuses on near surface accuracy. So you can see surface is reconstructed properly, but the interior field is not accurate. While when you use only iconal optimizer, the SDF prediction fails. So this is an ablation study done on the encoder architecture. Instead of using a local conditioning, we replace it with a global conditioning as done in the deep SDF architecture. But both quantitatively and qualitatively, it was observed that the result is not good. So this is what we get when we do only a global conditioning. This is another ablation study done on the activation and positional encoding. So clearly, Fourier encoding is required to preserve sharp features, but still we couldn't preserve all the sharp features. Yet removing the Fourier encoding increases the error and L1, chamfer, and Hausdorff. So this is again visualized qualitatively. So this is one failure case that we observed in presence of sharp corners. So the SDF prediction is smoothened out. Another failure case is in presence of very thin structure where the SDF prediction is inaccurate. So you can see here a thin needle kind structure where SDF prediction is inaccurate. In summary, we created generalized neural SDF for 2D point set with accurate interior SDF. Through experiments, we showed that full domain exact supervision overcomes the reliance on regularizers like iconal, and this generalizes to unseen shape without any test time optimization. It also supports robust medial axis extraction. It is stable under noise, outliers, and missing regions. In future, we aim to work at 3D by creating this data set based approach, and which will reduce the reliance on optimizers, thereby improving the training time and the inference time. Thank you.
Thank you so much for keeping time there. Very interesting work. And you've got some questions. Well, I'd like to ask, what happens on the representative top so that we have a whole house. Would you also be able to recognize that?
Your question is how you represent shapes with holes
Yeah.
in the ground truth, in the training data.
Yes.
We couldn't do that. In the future, actually we can do that in 3D. We have already done 3D work also. In the 3D, we created shapes with holes using B-spline surfaces. Are you asking that? The ground?
Recognize the fact.
You you could see this result, right? This the network is predicting this. The network is predicting the yes. But we didn't have this in the training data.
Yeah.
But network predicted it accurately.
Nice.
Mm.
You got the microphone.
So I was with my about the inside. So you say we are leading on the ball with therefore it's fish. But I was wondering, so if I compare to let's say more additional euro is different functions, they are praying for only new shape. They are retrained units. But here you need to have like a lot training on the lot person. How long is this first thing?
But the training is done only once, right? Yeah. Yes. This training took close to 3 hours. Yeah, just that. Yeah.
And then it starts sections.
Yes.
What about the inference stuff?
Inference time is 0.18 seconds. Yeah, it's there. Yeah.
Nice.
Yeah.
I think this is curious. I'm wondering about short complex forms where the meaning packs those like the words. How is these like do you get a nice line or use straight words? You have some maybe
Yeah, I think we have results. Corners, right? You're asking about sharp corners?
Right. Like the things. Yes.
where the video has those
Yeah. But few corners get smoothened out. That is one limitation we observed. Like the professor who talked in the morning, we also face that difficulty. Maybe we'll have to find strategies to solve that issue. I think. Huh?
first. Yeah.
Yeah, but that is captured, right? Okay. Thank you. Yeah.
You have questions?
Please ask me from top.
Okay.
Thank you very much for this wonderful section. Actually, I just wondering, actually, I know that it is quite difficult to calculate according to how many geometry you have in the and outside geometry. I mean that, and you show that, I mean, some geometry is more. And actually, and then that geometry, my English, the account of the geometry to be side and how effect your
Okay.
and the algorithm. Given that when I write more than 5 geometry, and that's I get the error, and so
Okay.
it's quite
Hard, yeah, maybe. Yeah. Actually, we could have tested that. I think we do not have that complex inside outside whole cases, right? Maybe I'll go back and test that. Yeah. 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 Thank you.
Thank you.
Thank you.
So the next paper is the problem that we use for learning students.
Hi everyone. Thank you for today to coming to hear this section. And I will present far from the boundary fields, a field design for the non-solids that are cut object into the unknown numbers of the pieces. This kind of driving application is a brittle fraction, but the representation is general. So any task where a network must learn a segmented implicit solid can use it. My journey and our journey and exploration for this thing was starting from the brittle fracture in games. At that time, I worked for a game company to just build such kind of the brittle fracture animation pipeline. So brittle fracture is an instantaneous, no plastic deformation. So think about the grass and also ceramic and also rock. Such kind of existing roots to get such kind of shape sit at two extremes. First is the physical simulation. We give the realistic fracture surface, but it takes maybe 20 minutes to 5 hours to proceed. So also for the Voronoi prefecture pattern runs in the tenth of the second, but such kind of shape are monotonous. So we want to both release and also the speed of the geometry generation. So we try to explore such kind of technique via the deep learning to learn the segmented implicit solids. That's that kind of the object we want a network to represent a solid broken into pieces. The fragment counts varies per example, and also the pieces are homogeneous. But unfortunately, there are no such kind of natural levels can do that. So the closest techniques in the conservation is a kind of the levels and also masks we use in the image learning. So why can we borrow this kind of segmentation to these tasks? The answer is that levels assume a fixed and meaningful class set, but fracture gives the variable numbers of the interchangeable pieces. So a level target is impulse. What we need is a continuous scalar field, and that field must satisfy three requirements. So first is that we need to just separate the arbitrary numbers of the homogeneous fragments. For second, the chain stability on the MLPs and also the neural implicits is needed. For third, round trip back to clean leak-free meshes is needed. So these three structure will structure the rest of the talk. So on the starting point, we just found a scientism field. The name called GSSDF, but we just think this is a simple scientism field with an external flip. So we give a new name, but actually it is totally same as the scientism field. So at every point, we store such kind of distance to the nearest fragment boundary. Such kind of boundary becomes the zero set, and the entire segmentation lies into the one continuous level-free field. So with this representation, the requirement the first requirement is done, but there's still two problems remain. So when we actually chain on it, two problems appear. The first one is that the small fragment vanish. And also for the second, the MLP chaining is unstable. To solve the problem one, a small fragment spans a tiny distance range. So the 0 to the 0.1 can just be the main of the part of the values, while a large one spans in the full range. Sampling also regression barely sees the small values, so the small fragments simply disappeared. To this problem, the fixed solution is to renormalize each fragment to the full 0 to 1 range. So for the second problem, the interesting signal lies in the right on the boundaries, where the fields turns over sharply, but the uniform sampling expands the network's capacity on the flat interiors. The fixed solution is to just concentrate training samples near the boundaries, which is a common sense for the such kind of training technique. So putting both such kind of physics together with the FFBF, for each fragment to find such kind of point farthest from the boundary deficit in the interior, and use its distance as the normalization reference. So look at the left part in the figure. Under the GSSF, the small fragment peaks well below 1. So it's a kind of value like 0.4 or something like that. But under the FFBF, both fragment peaks at exactly 1. So small pieces survive. So boundary also stay sharp. Training should be stable. So according to this design, the requirement first 1 and 2 can be satisfied in the same time. So on the continuous neural interfaces, the full recipe is that we use the MLP plus the boundary-centric sampling and also plus the FFBF normalization. So you can see that after the ingredient effects for the A, a plain MLP on the GSSDF, the boundary is blurry. So after we use the B, the ones that adding the such kind of the boundary resampling, it will become better. So after C, by adding the such kind of the FFBF normalization, the fragment separation becomes crisp. And also, there are two findings we can find in such kind of the chaining curves. First is that for the if we use a FFBF, the convergence will be faster than the according to the random results. Instead of fewer inputs than the UDF and also chunked UDF or the GSSDF. So and also second, just as useful in practice, because every fragment occupies the full normalized range from zero, maybe -1 to 1. So the loss value becomes a reliable indicator for whether the field is actually being learned or not. So with the baseline, a lower loss can just hide such kind of the fragments that were never captured. The loss looks good while small pieces are silently missing with the FFBF. If the loss is down, the fragment should be there. And this is also the method we use for the reconstruction. So the flooding will just go to the step by step to just make the value from the 0 to the 0.01 and then gradually just change the threshold. After that, each kind of the part will be separated by with this kind of the procedure. So after the procedure above, the requirements 3 would be done. So back to our meshes, we compared against UDF-based extraction pipelines, such kind of the CAP UDF, also mesh UDF, and also the NDC. The top row looks plausible for the outside, but look at the interior cuts on the both the bottom row. The UDF, the pipelines leave the noises also shutter interiors. FFBF with the simple flooding algorithm will recover clean, also watertight fragments. And with a small exploration of that, you can see that the fracture pattern will closely match the BEM reference on the right part. But actually, since the capital UDF, also mesh UDF, also NDC, it's kind of the single phase, single material extraction. So the comparison is unfair. But actually, you can see if you use a child to choose such kind of multiple extraction, there are few techniques we can use. So the flooding with the such kind of FFBF should be reasonable. And also to quantify it, we use we call it MFCD, which means the multiple fragment transfer distance. Since there are few such kind of measured, we just design our version. So the transfer distance computed per fragment. So a method that jumps small pieces is a panelmass. The number we can see the GSSDF collapsed to the 12 fragments against a ground truth of the maybe 48 FFBF recovered from the 47. The small pieces are back, and the cost such have the FCD from the 0.38 down to the 0.06, with the one weight scores improving similarly. And also, we do this have the corrected comparison. Such kind of experiment before depends on the maybe 50 case data set. So for the such kind of this kind of experience, we use a 50 case data set. The loss also random result will be converged in the end for all of the such kind of representation. But in the case we use a full data set, which in the existing paper with the 500 data sets to train, the difference become more obvious. So GSSDF with the maybe 500 case data sets are noisy and also broken. Once we use the FFBF, BDF, and also the MLB, and also the boundary resampling with the 500 different cases, we required coherent fragments close to the ground truth on both the square wave and also the Bernie model. So also the FFBF is not such kind of a fracture specific representation. It is a numbing target for any solid divided into the homogeneous region of the unknown counts. A runtime destruction in games and VR can work. Also, the multi-region autonomy in the biomedical shapes. Also, the cell segmentation may use it. And also for green structure forms, and also CAD part decomposition, also in the 3D printing in different material may use it, but we have tested little, but actually not so far away. So one takeaway for such kind of recipe is that for repetition, we can use an FFBF, which means the per fragment far from boundary normalization. So for chaining a plain MLP with the boundary resampling, and also you can just a faster conversion and get a loss that you can just actually trust. For reconstruction, use the flooding. Also, we can get such kind of watertight fragments. So one level 3 continuous fields for such kind of arbitrary numbers of the homogeneous pieces can just earn from this kind of practice. So there's still such kind of limitation here. So first is the per object chaining, there's lack such kind of generalization. And also there is no fully real time at the high resolution, something like the 256 resolution. And also for such kind of solution, we need to just develop such kind of continuous representation between the multiple segmented implicit pattern. So we can just try to just develop such kind of representation, and also need to some speed up also needed for this in the future work. So to summary, the FFBF is a simple idea, just try to just normalize by the such kind of farthest from the boundary point, and that will just turns a otherwise few points segmented implicit target into something a network can just know. So small fragments will be preserved and also fast and also transversely chaining multiplying mesh can just recover. Thank you for to hear this such kind of presentation, and I'm very happy to receive this such kind of question.
Thank you very much. Very impressive results. Maybe we've got some questions. Okay. Yes.
Mhm. Oh, yeah. So the output representation, we just design such kind of the representation as output. So for the other pipeline, we try to do is a kind of the we use such kind of the vector as our input. So it's kind of the conditional vector as input, and also the output should be such kind of the segmented representation. Yes. Yes. That should be a question that I just do such kind of the habilitation study. But actually, what we found is that all of the such kind of the activation functions work. So there seems few difference. According to the paper, we just try to do the ablation study, and Silu and also the serum is worked.
Any more questions? I have one. I noticed that your segmentations, the final result was one color. Have you looked at texturing and what happens when you try and texture?
Yes. Yeah, and that should be the lack of this paper, but actually I think it can be used for maybe different technique to just do the more than the geometry, but also the texture. But we still fail to just do the extension external work for this to just including the texture. I think it will be done in the future.
Yeah, they definitely.
Yeah.
On that.
Oh, please let me to take a refer.
Well, thank you very much.
Yeah.
And yeah, yes, as well in the past. And one thing about this one, when you see your previous stall as well,
Good. Thank you for the presentation. Yeah, I'm actually those are my supervisors, and I guess that Eric Galin was your student at some point. So quite funny to be there. All right, so I will now present you our paper, Extreme Continuous Level of Detail for Skeleton-Based Implicit Surfaces. As you all know, implicit surfaces, I guess, let me just quickly recap the motivation. Those are really nice this is a really nice formalism to represent surfaces. It enables really a strong editability of those surfaces, as well as really precise small details. Yeah, however, those are not free to compute. For instance, the dinosaur that you can see here is made of more than 200 bones, and to compute implicit surfaces, you need to process the implicit function lots and lots of time. So for each bones, you need to compute lots of computation and everything. So it's quite long. That's where our approach comes in, to introduce level of detail to simplify the shape, smoothing out, to enhance the computation capability of 3D scenes using implicit surfaces. So our approach achieves between 1 or 2 order of speedups in the rendering time for various types of models, as well as reducing the aliasing of the smoothed out surfaces. And we are currently the only level of detail approach that is enabling topological changes in the surface to really go to the extreme simplification such that everything becomes an ellipse at some point. When everything is only 1 pixel wide, you don't really care of details anymore. So, obviously, level of detail is not new in the study, and it has been implemented for implicit surfaces a long time ago. For instance, in the case of blob surfaces, we already have method to compute level of detail. However, the transition between the details as well as the generation of the actual surfaces are not yet automated for the blob surfaces. Later on, we've introduced normal warping that adds back the details on the smoothed surfaces, taking care of the transition, because if you don't really see the transition, there's no need of transition anymore. However, still the level of detail needed to be computed by hand, so that's quite tiring. Closer to our concern on skeleton-based implicit surfaces, there's absolutely no traditional approach to simplify the skeleton. However, there's what we can say reversed approach that we try to adapt detailed on an already smooth surface, like the work of Cedric Zani, for instance, that will add a small patch of details on the overall surface to create some cracks and nice features on the surface, as well as the one of Angelidis that subdivides recursively the skeleton to smooth out even more the surface as the camera goes closer to the object. All right, so that is absolutely the opposite of what I will be presenting now, because what we are trying to do is to get out of the surface. Quick recap about the underlying mass of the implicit surfaces. So those are potential that are being integrated over a skeleton. So the skeleton represents like the idea of the shape, and the integration will inflate it and create the smooth surface in the end. Quick recap. Implicit surfaces are defined as a level set of a continuous function, and usually you are quite free to use whatever function you want. Simplest of all being the blobs. It's quite an old model, and it's quite nice for its parameterization, because you have radius control over all the primitives that are themselves being represented as distances to some skeleton, either point, segment, or triangle, or whatever you want. And those distances are then, and that's usually forgotten, are then converted as a potential, giving a new degree of freedom in the resulting shape, because to convert this distance, we use kernel, and those kernel are being parameterized by a width that will be important later down the line. And finally, the last parameter that is always being forgotten because it's always being put at 1.5 is the ISO level, targeted ISO level. For this, our method, we choose to actually alter this ISO level, targeted ISO level, so it's good to have in mind that we can actually play with the entire set of parameters and not only the radiuses and the points. All right, so that was for the blobs. Unfortunately, they suffer from the bulk effect, meaning that when you have lots of blobs near each other, their potential will sum up, creating some bulks that are highly undesirable. To palliate that, we can integrate the potential over the entire skeleton, which take care of the smooth blending of surfaces. However, by doing that, you also integrate the radiuses along the skeleton, losing out the control that you had previously on those radiuses. And finally, so to palliate this last issue, we, for this paper, are using the scaleless convolution surfaces that normalize everything depending on the radiuses and enabling very sharp details on very smooth and wide surfaces. However, this is not free, as both the number of primitives and the complexity of those primitives do create some computation time and slow down the process. So that's the goal of our approach, to decrease the number of primitives as well as their complexity. All right. So now will be the overview of our methods. The main diapositive that you want to memorize is this one. We start with a simple shape that we want to simplify to speed up everything. Our pipeline works as follows. That's a three-step framework that starts by inflating the shape to smooth out the details, change the topology, and basically simplify everything. Then, because this is not accelerating anything, just inflating it, we remove some useless bones to actually speed up the process. And to keep everything nice and tidy, we correct the inflation, but through the mean of a deflation on specific axes. And if everything is done nice and well, the resulting shapes should be really close to the pruned shape, as you can see. All right. And finally, because we want to achieve nice runtime timing, actually, our pipeline is fully pre-computed to really just care about the rendering during the rendering process, meaning that both the inflation, the pruning, and the deflation are being parameterized through a single level of detail parameter that we call lambda, and that it goes from 1 to draw the original fully detailed shape to 0, which will draw an ellipse, roughly, because in the end, everything is elliptical. All right, now for the details. The inflation is being performed by both jointly decreasing the targeted ISO value that is usually forgotten and increasing the kernel width of the kernels. This has the effect of inflating the shape at the expense of increasing the volume and losing the aspect ratio, as we'll see later, but that's for the deflation step. This is the simplest of all. Then we want to actually simplify the skeleton to speed up the process of computing the shape. To do that, we introduced a dynamic skeleton that will evolve during the variation of lambda, meaning that for a level of detail parameter, a given one, we know which drone to compute and to process, and which drone to erase and to discard. And to compute those, we iterate over 3 operations, namely the deletion. If at some point during the inflation process, a primitive becomes negligible compared to another one, we allow ourselves to just remove it and avoid it. Then the merging operation, the collapsing operation, if at some point a primitive really looks like a point because it's being so inflated that it's really spherical, we allow ourselves to remove this primitive and replace it with the corresponding point. And finally, if 2 points are really close to each other, once being inflated, then also we allow ourselves to remove those 2 points and replace them by a well-chosen single point. In both 3 cases, we either decrease the number of primitives or the complexity of the integration of the potential. So we reduce the computation in each cases. However, the inflation does alter the volume and the aspect ratio of the shape. As you can see here, the ellipse under a uniform inflation turns out into a sphere. So that's not what we want, and to palliate this, we introduced the level of detailed axes as well as anchor points. So those 2 notions, the level of detailed axes are simply the principal axis by default of our shape. This can be tuned manually if the artist wants it, but by default, we decided to say, oh, let's get the shape, an intuition of the shape by using the principal axis. And the anchor points are simply the intersection between the shape and those axes, meaning that and we want to keep those constant in space during the entire process. So originally, those anchor points are being defined by the original surface, and as the surface will inflate itself. We will downscale, we will compress this inflated shape along those three axes to keep the anchor point fixed in space and preserve the overall aspect ratio and volume of the shape. All right, so I will let you admire our smooth transition of shapes. As you can see, we are able to consistently smooth out the shape in a natural behavior. The topology may change, as for instance, the Scorpio passed from a sphere-like topology to the donut one with a hole when the antenna link with the tail, and go back to the sphere one when it become a simple ellipse. We are able to achieve between 1 or 2 order of magnitude of speedups for the most simplest level of detail, smoothing out the surface and reducing the bones. And during the smoothing out of the surface, we also reduce the aliasing because less detailed surface is less susceptible to aliasing artifacts. We consistently decrease this aliasing features, not features, problem issue in all of our test phase, and especially for the dinosaurs one, we are able to halve the aliasing. All right. So to recap, we are the first level of detail approach on convolution-based implicit surfaces, achieving between 1 or 2 order of magnitude in the speedup of the rendering time, while decreasing the aliasing. And furthermore, we are able to really simplify to the extreme the shape by enabling ourselves some topological changes. However, there are some limitations, the main one being that because we're inflating the bones, we are currently not compatible with bounding volume acceleration techniques, because those suppose that the volume stay fixed in space. So this is the main limitation, and as a future work, we may think of some acceleration, inflating bounding volume hierarchy-like structures that will be able to match the inflation pace of our surfaces to speed up even more the processing of those. And furthermore, as everything is being pre-computed, we are currently not able to animate the resulting level of detailed shapes. For that, the only piece that we can think of is to have some robotic animation, in like we will compute the level of detail of the arm and only animate the arm uh, only like separated parts. All right, thank you for your attention, and I will now be glad to take your question.
Well, it was lovely talk. I do remember talking to Eric about level of detail many, many years ago, but we never did anything about it. So
Yeah,
it's great
thank you.
to see you've done this work. So I'm going to jump into my question first. If this does happen. And one of the things that was interested in then and now is the relationship, the distance and length. So if you've got a linear relationship when you're moving the camera, does that work? And you have very good results when you just use a linear relationship.
Yeah, actually, we are using a linear relationship, meaning that we have a threshold between at which point we will start the level of detail simplification and an ending threshold at which we will end it. Otherwise, if we really, for instance, if the lambda parameter goes to 0, everything explodes for division by 0. So we stop it at some point. And for now, it's really just a linear relationship. We sort of actually doing some evaluation of the area of the shape appear on the camera to try to minimize the aliasing, for instance, to try to optimize and better link the level of detail parameter to the distance to the camera, but it did not went anywhere. So that's for future research as well. But we sort of it, and for now it's just a linear relationship.
Okay, thank you. Can you continue to remember? Yes. Very good. I have a question. That is the news. right?
Yes.
And then if you want to have this level of moving path, is it a far step to try to get this to run on the real time for animated solutions, or is it not possible?
The difficulty is that our pre-computation is in n square, no, not square, cube towards the number of bones. So if you have a really simple model, it can work. But on those models, it takes roughly like 30 seconds on an average CPU to process. So it's not run real time anymore.
What made me explain that you have these different rendering algorithm shop less serious, more simple, more complex. This was the motivation of those. I was wondering when you simplify the maybe the end shape is so simple that you don't need the more complex rendering algorithms. If you consider also during simplification, swapping the random use case only for very high level of data.
Actually, we did not consider that. That's actually a good direction for future work, especially because at some point, and we can actually measure it, everything turns into an ellipse. And when you have a crowd simulation, there's actually a lot of elliptic. So that's definitely a good future work aspect for future research. But yet, we did not thought of that.
Any other questions? Okay, I'll just speak again. You're really insistent. That's
Okay.
learning improves skeletons and communicates new impressive knowledge.
So good afternoon, everyone. I'm Bincy again from IIT Madras, and my advisor is Professor Ramanathan Muthuganapathy. So the previous talk was on 2D point sets. This noisy 2D point set. This is on noisy 2D images. So before I start, I explain what a skeleton is. Here our input is a 2D shape represented as binary image, where skeleton or the medial axis is a thin center line abstraction of the shape, which is topologically and homotopically correct. By topology correctness, we mean the resultant skeleton should be connected and it should capture all the junctions. By homotopy preservation, we mean it should capture all the holes. It should, if the shape has a hole, the resulting skeleton should have a loop around it. The core problem with the medial axis or the skeleton is its sensitivity under noise. Small perturbations on the boundary can create a lot of insignificant branches like this. So this represents a clean shape with a clean skeleton. This represents a boundary which is perturbed with noise, and this is the resulting skeleton. So this makes the skeleton unuseful. The usual approach in the literature is to assign some significant measure to the resulting skeleton after you extract the skeleton. So this is a significant measure called the vanishing angle. After you establish this significant measure, you have to prune at some threshold to get this clean skeleton. But the issue with this kind of thresholding is this requires manual intervention, because if you use the same 50-degree threshold, For this flower shape, you lose many of the important features. So calling it appropriate threshold for this shape is 45 degree. So this calls for manual intervention. So these are different significant measures in the literature. Each of them has its own pitfalls. Some of them do not completely remove all the unnecessary branches, while others do over prune. So in the literature, there are few approaches for actually one approach for learning skeletons in a supervised manner. So this was one data set that was released as part of a CVPR challenge, but this is no more publicly available. And also it is not suitable for a pruning task because you can see many unpruned branches still exist in the data set. So our motivation was to go from a noisy shape directly to a pruned skeleton by learning it. So we already had one paper in SIGGRAPH Asia as technical communication last year where we were trying to go from a noisy shape to clean skeleton, so called ConfBSNet, but it had junction breaks. So that to avoid this topology break, we are proposing a topology aware junction preservation loss. The major contributions of this work are, since skeletonization is used in graphics and interactive application, we are focusing on improving the inference time of our skeletonization approach compared to the previous work, and hence we create a compact model which is 1,000 times smaller than a teacher model. We distill from a base 64 unit, which is called the teacher model, to a base 2 student, which is called the student model. The student model now has accuracy as close as the teacher with 1,000 times fewer parameter and being 6 times faster than the teacher. And since there is no common evaluation benchmark for evaluating the skeletonization problem, we created a human annotated noisy shape clean skeleton benchmark. So this is the data creation process. We use spline curves to create various geometric shapes, and then we rasterize them at high quality so that we get clean medial axis. So this is done under expert supervision. So this entire process shows data creation for one sample. After this, we add controlled noise to the boundary. This is also done under expert supervision because adding noise shouldn't add a new feature, so thereby bringing in a new medial axis branch. Hence, after we add controlled noise, we maintain the skeleton of the original clean shape. So this gives us an appropriate data set of noisy shape, clean skeleton pairs. So this is the architecture of the teacher-student network. The teacher is a base 64 unit from which we distill a base 2 student. Now, at all these levels, we transfer knowledge from each of the layers of the teacher to the student. This is feature distillation. And now at the output, using the KL divergence laws, we transfer the soft labels of the teacher to the student. And also, to preserve the topology, we propose the junction preservation laws. So as I mentioned, we go from a base 64 teacher to a base 2 student. You cannot directly go, so there will not be stable knowledge transfer if you directly transfer from the base 64 teacher to the base 2 student. Therefore, we use intermediate teachers and do a sequential knowledge transfer. So this is why a junction preservation loss is important. This figure shows that we have shown T, Y, X and plus junction. You can see these red pixels show the removed pixels. In this case, we have lost 3 pixels from the endpoints. Same 3 number of pixels are lost from the junctions. But for skeletonization, this is more catastrophic. Losing 3 pixels from the junction leaves a structure disconnected. So this is more catastrophic than this, but only by binary cross entropy loss, if you take, will treat them equally. They will consider them as 3 missing pixels. So to detect missing pixels, so we propose this loss, which is able to detect missing branches and spurious branches. So you can see this. So same tips when shortened, the binary cross entropy loss is not able to, or the dice loss is not able to capture that in loss, while the junction loss is able to capture that. So this is the entire loss on which we train the network. So total loss consists of the distillation loss and the task loss. Task loss is now a combination of BC, dice, focal along with the proposed junction preservation loss. And during distillation, we do transfer the features at all levels and also the output soft labels. So this is the process of creation of the evaluation dataset. We collected noisy shape from 7 shape benchmarks. Then we create, using distance transform, we created the skeleton. So of course the shape is noisy and the resulting skeleton has noisy branches. Then 5 annotators manually clean the skeletal branches to create a clean skeleton. After which we reconstructed them to ensure that this skeleton has all the significant branches to reconstruct the shape. So this serves as the evaluation dataset. So these are results on the evaluation dataset. So the first row shows the result of the classical medial axis. So these are results on complex junctions and even shapes with holes. This shows the noise robustness of our result across different noise levels. You can see our approach at the bottom is able to produce the same stable skeleton. So while the medial axis produces insignificant branches. So we compare with different learning-based approaches. So all the large foundation models and the big networks overfit on a small skeleton dataset like ours, while the small networks like mobile net, efficient net, squeeze net, etc., do not accurately predict skeleton also. This is the conf-BS net that our prior work, which had small junction breaks, and the last column shows our result. So the major problem with the large network is since they overfit, when they are given new shape, they do not generalize proper. So this result shows how a distilled model performs in comparison to a scratch model. When you take a base to scratch model, you can see the prediction is fragmented and noisy, while the distilled model has good predictions. This is a quantitative comparison with the classical approaches. All the classical approaches are geometry based, and hence you can see the computation time. Uh, it may be noted that they run on CPU while we run on GPU. We require only 0.56 milliseconds. So while the teacher takes 3.52 milliseconds, the student takes only 0.56 milliseconds to predict the skeleton. So these are qualitative results. As I already mentioned, geometric approaches call for a manual intervention. So this is quantitative comparison with all the learning-based approaches. So you can see the average effort score for a base 64 teacher is 0.697, while that for a student is now 0.693, showing that we have effectively distilled the knowledge from the teacher to the student. And look at the inference time. The teacher takes 3.52 milliseconds, while the student only takes 0.56 milliseconds. And these are the results. Of course, large model takes more time than even the teacher unit. So this is again the same plot. You can see we have the least inference time and good F1 score. So this is the ablation study done on the different configurations and also on the distillation configuration. We distill on the distillation weight and also the temperature. An important thing to note is that removing the junction preservation logs result in a dropping of F1 score from 0.762 to 0.55, showing that the F1 score is indeed contributing to the accuracy. So this shows how distilled model wins over scratch model over all levels. So this shows base 64. This is base 32. You can see at all levels, distilled model is performing better than the corresponding scratch model. So during experimentation, it was observed that a weighted binary cross entropy loss is required to efficiently transfer knowledge. So with classical binary cross entropy, when the FN score is only 0.587. So showing that for an architecture of this kind, where you want to do distillation of almost 1,000 times, a compression of almost 1,000 times, there were two design strategies that we observed. One was using this weighted binary cross entropy, and the other was the batch normalization. So these two, although might seem like two small things that we do in deep learning, but contributed a lot to our result actually. So this figure shows that the resultant skeleton is preserving all the important shape features. This is shown through reconstruction. So this is one failure case in presence of high ligature regions. For example, you can see a junction break here. So this is one failure case we observed. In summary, we created a distilled base 2 student model from a base 64 model. The student model is only now 31K parameter, and this 1,000 times smaller than the teacher, and while being 6 times faster with comparable FN score. The junction preservation loss ensures topological correctness. We could observe that large and foundation models overfit on small data set like ours, and we have created practical and real-time skeletonization strategy for interactive and edge deployment. Thank you.
Maybe we certainly have time for one or two questions. So I was very impressed with the how far the neural nets have come to actually give you these kinds of results. And I did notice that you compared to a large number of other models.
Yes, yes.
So in doing that, did you learn anything from looking at these other models? What was how did you know this approach was going to be better than they were when you started?
Yeah, honestly, I didn't know that the small networks are going to be this capable. Uh, but one thing was that we started with the whatever compute we had in our lab. We wanted to show that geometry problems could be solved using the learning, but that is democratized for whatever computing resource that we have. So we did compare with large models, and we found that results are not very good. And then, yeah, that was a promising place. Then we thought of design strategies. So then we could learn more about improving the networks using small architectural changes. So we focused more on smaller architectural nuances, which could actually do a lot of improvements to the result than just picking the model, giving all the data and looking at the result. We worked on the architecture because we were forced to work because that was we had limitations on the computation side.
Well, it's impressive to me that machine learning has come so far. Thank you very much. Maybe there's small questions from everybody's very keen to get to the correct. So, okay, I'd like to thank all the students in this session. And